All right, gang, final video in lesson number 4, I believe, discriminant function analysis. And I didn't see any reason to reinstall everything. So what I did, I'm just going to start right here. So instead of using the jackknife approach as I did in the previous video, another acceptable approach would be the train test approach that I've demonstrated previously. But recall that we need at least 4 cases per independent variable. So we have 3 predictors here, ACT, SAT, and state score. So the theory tells us that I would need at least a sample size of 12. So what I did is I just went ahead and set n to be equal to 12. So I, again, I have a 19. So my test will consist of 7 randomly selected subjects. And my train is 12 randomly selected subjects, which I start right there. So the next thing I do is, just as I've done before, create what's called my train sub data set, and then set up my train data set by taking the full data set and just looking at the train sub. And the test, I look at the full data set and subtract out the train sub, leaving me with the other cases. Run my model, and you can see a little different. First of all, you can see the difference in the prior probabilities of groups because we're not using the entire data set. So of the random selection, 42% of the students, I should say the random selection for train, 42% were from District A, a fourth from District B, and a third from District C. Group means, again, good to report, and we get the linear combination of these values, which makes up function 1. Linear combination of these makes up function number 2. Proportion of trace, I believe that's a little different than we saw before, as you would expect. It's a different data set. Next thing I want to do is get into the prediction component. And you can see that instead of describing like 93 or 4% as previously, this approach, we still get an impressive classification percentage of actually classified cases, very high at 86%. Now, the other plots that I would create, for some reason, when I run this plot right here, I thought that this would give an array of plots. So it would compare 3 to 4, 3 to 5, and 4 to 5. But for some reason, well, it does temporarily, but I don't know why that doesn't stay. But anyway, this compares state and SAT, which is my third and my fifth. If I wanted to compare, which I would, the fourth and the fifth, I would just run this. And if I want to compare the what's remaining, third and fourth, I would run this plot. Again, the plot that I prefer is the simple one, this one. And again, you can see that the regions would be clearly defined. I would think that we would have a linear function right here, and then another linear function right there, with only C being. So it didn't do that, did it? Huh, that's interesting. Well, no, I'm sorry. This is, yeah, this is on test. So it must have, yeah, I'm not sure. Um, Interesting. I gotta work on this. I gotta see what's going on. I want to get a screenshot here. Let's just pop this out right here. And then let's do some drawing. Sorry, I'm on a tangent. So I think obviously we're going to be running a linear function from here to here. But I'm just curious where the others will be. Um, oh, I bet it ran this. So we have, huh? Yeah, I have no idea. I don't know what it was doing behind the scenes because it looks like to me that we could create this where there's only one error, and we can see that there were more than one error. There was one error. What am I thinking? Okay, my bad. I thought there was something. I'll lose my mind. So anyway, I think that's the way that the classification accuracy actually played out. All right, sorry I wasted your time. Take care.